Today we're going to talk about exponential functions. Now, previous to this, we had talked about linear functions, and if you remember, when we talked about linear functions, we talked about them being in a couple of different forms. One of the most popular forms was the slope-intercept form, or y equals mx plus b. This is a linear equation. Okay, we're not going to be talking about linear today, we're going to be talking about exponential. Exponential is a little bit different. It comes in this form, typically y equals a times b to the x power, where a is not a zero number, not a non-zero number, b is greater than 0, and x is some real number. And what's most recognizable about a exponential graph is they have a couple of possible shapes. Exponential functions tend to have a very particular shape. They can either look like this, almost like a plane taking off this way, or a plane taking off this way, or they can look like this, sort of the mirror image of that. Now, these aren't any particular exponential function, but generally this is just the options for their shapes. And there's 4 different options there, right? There's options of it moving in this direction, there's an option for it to do this, and it's only one of these 4 options of the general shape for the exponential function, which is different because we're used to linear functions. Remember, linear functions look just like a straight line. Here we have 2 separate functions, one of which is linear and one of which is exponential, and we're going to talk about how to know the difference. With this function, notice that the x values each time have what we call a common difference. They're increasing by 1. That's a common difference. The common difference is increasing by 1. The y values, however, don't seem to have a common difference, right? This is decreasing by 2, decreasing by 6, decreasing by 18. So there's not this common difference here. But what they do have is what we call a common ratio, because if you pay attention to the multiplication or division that's going on here, you can see that the same thing's happening at each step. If I multiply by 3, I get negative 3. If I multiply by 3, I get negative 9. If I multiply by 3, I get negative 27. So the function on the left here has a common difference for x and a common ratio for y. Okay, let's look at our other function over here. Again, x has this common difference, and it's the same common difference, just plus 1 each time. Okay. Let's look at y. Y, in this case, actually doesn't have a common ratio. If it did, and we multiplied anything by 0, we just keep getting 0 and 0 and 0. In this case, we actually have a common difference. Add 3, add 3, add 3. Okay. Because we have a common difference on both, we know that this is a linear function, and we know that its slope is y over x, so its slope is 3. Okay. So the common difference and the common ratio result in an exponential function. This is an exponential function of some sort. If we have common difference on both, this is a linear function of some sort. We're going to have to graph these exponential functions, and one of our easiest ways to graph a function is to do it by filling out a table. So let's say we have the function y equals 3 times 2 to the x power. And this is what an exponential function looks like. See how x in this case is in the exponent position? Okay, that's an exponential function. So if I were to start making a table for this, x, y. What happens if I plug in 0? Well, if I plug in 0 here, I get 2 to the 0th power is 1. 1 times 3 is 3. So 0, 3 is a point on this graph. If I plug in 1, 2 to the first power is 2 times 3 is 6. Notice, again, common difference, 0 to 1, common ratio, 3 to 6. We can imagine what's going to happen next, right? If I make this 2, 2 to the second power is 4 times 3 is 12. So my common ratio on my y is times 2. We can also do negative numbers. So let's look at what happens when we plug in a negative number. Y equals 3 times 2 to, let's say, the negative first power. Well, 2 to the negative first power is 1/2. So y equals 3 times 1/2, or y equals 3 over 2. So that point would be negative 1, 3 over 2. Getting pretty small. And in fact, the more negative we go with our numbers, let's say negative 2, we're going to end up with 3 over 4. Negative 3, we're going to end up with 3 over 8. Closer and closer to 0. So that's what happens when we start plugging in negative numbers to these exponential functions. We end up with closer to 0 values for y. Not more negative. In fact, no matter how negative we make our x values, we're actually never going to make a negative number. We're never going to get there. We're only ever going to get closer and closer and closer to 0. So that's how we would plug in and start a table of values for this exponential function. Why don't we graph some of these values? 0, 3 is pretty easy. 1, 6 is good there. We're going to run out of room for 2, 12, but we can come over here and do negative 1 and 3/2. Let's see, 3/2 is 1 1/2. So negative 1 and 1 1/2 would be right about there. Negative 2 is 3/4, so not even all the way up to 1, just more than half. Okay. Negative 3 is 3/8. Now we're less than half. Close to, but less than half. So right down here. And you can see the shape that this thing is starting to make. Right, you're going to end up with a line down here that curves up and then increases exponentially. Like that. So that gives you an idea of how to plug in and how to graph an exponential function.